Hello, my name is Marcel Lewandowski. I'm with the University of Minnesota Water Resources Center. The title of my talk is Linking Soil Health and Water Quality. So those of us working in the fields of natural resources and conservation intuitively understand that soil and water processes are tightly linked. But despite this understanding, we don't leverage soil health principles as much as we could to manage water resources. And I see two barriers to practical applications of soil management for water management. First is we have only a weak understanding of the physical mechanisms and processes by which soil properties add up to water resource impacts. And secondly, we don't know real well how to measure or relate field properties and water resource properties and make those connections statistically, empirically. We can find studies that measure the impact of cover crops, tillage, and other field practices on water movement and properties. And we can find studies that document different soil health measures in response to these different field practices. But we don't have a good idea of how changes in dynamic soil properties might impact stream water quality and how those connect. So what are the mechanisms connecting soil and water? Starting on the right side of this graphic, water resource managers are interested in these attributes of water. They're interested in how water is partitioned into the various pathways in the water cycle. That is it infiltrated into the soil versus sheet flow on the surface versus channelized flow, transpiration, horizontal versus vertical flow through the soil, water detention in lakes and other micro and macro depressions, and so on. We are also interested in the rate of water, how fast it moves or it pauses along all of those pathways. And then finally, we're interested in what is in the water. The middle column lists soil processes that impact those attributes of water. And notice how these relate to the commonly stated functions of soil, such as regulating water, filtering water, cycling nutrients, and so on. Infiltration is how water enters the soil in contrast to hydraulic conductivity, which is how water moves through the soil. And that plus water holding capacity, you can imagine how those three processes impact the partitioning and rate of water movement across a field and across a watershed. And obviously chemical adsorption and desorption and all the myriad biological transformations impact what is in the water. So the left column, those are the attributes of soil that determine how soil functions. The structural characteristics such as the size of aggregates, the stability of aggregates, structure of pores, the size and type of organic particles, those kinds of structural characteristics, and then the biological characteristics, including both macro and microorganisms and roots. Of course, the weather, soil chemistry and texture, the shape of the landscape, agronomic practices, all of those landscape and management factors impact those structural and biological characteristics of soil. The puzzle then is how do we quantify these mechanisms and these relationships? And this is important because we want to we want to predict the impact of our choices. That is, for a given soil, landscape, and climate, what are the management practices that are going to give us the agronomic and water quality results that we want? And what are the trade-offs among the various soil functions? Do certain practices in certain contexts change one function, one direction, another function, the other direction, those kind of trade-offs? And then what are the trade-offs among various water resource goals? And the obvious difficult one is nitrogen versus phosphorus loading in water can be impacted differently by soil. So we begin to characterize these soil and water connections by first measuring a variety of soil and water attributes and then trying to define the relationships between them. So by soil health measures, I'm talking about soil organic matter, soil organic carbon, physical characteristics such as infiltration, aggregation, biological activity, the structure of the biological community, those kinds of things. Water quality measures, including sediment, nutrient levels, contaminant levels, pathogens, and flow volume of both, say, annual and event peaks, all of those kinds of characteristics. Regarding flow volume, to clarify where I'm coming from, I'm speaking from a Minnesota context where climate change, what that means for us is rising precipitation levels, both annually, annual precipitation, and the size of events. We're getting a lot more large events. And so a lot of our water quality issues are driven by increasing flow volumes. So that's what I'm thinking about when I talk about flow volume concerns. Now, once we've made these measurements of soil health and water quality, how do we characterize that relationship between those measures? And we'd like to think that water quality improves as soil health improves, as shown by the red line on this conceptual graph. But the shape of the relationship between soil health and water quality depends on which measurements you're comparing. For example, the blue line might represent the relationship between infiltration and phosphorus loads in water. As infiltration increases, do watershed phosphorus levels improve to a point and then plateau? Or conversely, nitrogen loads in drinking water might actually increase and get worse as infiltration increases, especially on sandy soils with high hydraulic conductivity. So even though we've got increasing infiltration, which is generally considered improved soil health, it may be having a negative impact on water quality. Consider some measures of biological activity. As activity increases, do nitrate loads decline at first, but then later start to increase if nitrogen cycling and the timing of it increases too much? One of the challenges to linking these soil and water measurements is how different the scale of measurement is for soil and water. And by scale, I'm talking about all three: location, frequency, and the duration of over which the measurements are taken. Location, soil is typically taken at a point, or it may be taken at many points and summarized across a field. Water is, on the other hand, taken at a watershed outlet or in stream, in which case those measurements are summarizing. A single in-stream water measurement summarizes what's happening across a whole watershed, whereas a soil sample at a point represents processes at a much smaller scale. Frequency of sampling differs here. Soil samples might be taken yearly or maybe a few times over the season. Water samples during a storm might be taken hourly or daily to characterize that curve. And then the duration over which these samples are taken. Are we trying to understand seasonal variation, or are we trying to understand interannual variation? So characterizing soil health across a watershed seems like it would require an impractical number of samples and pretty careful summary analysis of how do we summarize that to say the soil is this across the watershed. So instead, we often are doing modeling, or we're using land management practices as a proxy for the condition of the soil. Ultimately, we're left with scaling up problems. How does the water quality at the edge of fields, across a whole watershed, add up to water quality in the stream? So the result of all these research challenges is this, what I show in this diagram. And starting on that top group of ideas, the relationship between field practices and water quality, we've documented differences in how management systems impact water quality, at least at the edge of fields. For example, we can say that cover crops tend to reduce runoff or increase transpiration or reduce nutrient loss. However, these results are highly variable. And so we haven't defined how much of a watershed needs to be covered by a practice in order to reach water quality goals. And the third bullet there, we have a pretty good idea how to identify critical source areas where practices should be targeted. But I'm not sure if we know where to cite practices to most cost effectively impact the flow out of a watershed. Now, moving to the left side of this image, what do we know about how field management impacts dynamic soil properties? Again, researchers have documented differences in how management practices impact soil organic matter and aggregation and infiltration, biological activity, and so on. So we can measure those differences in any particular study, but these results are highly variable. And so we can't look at a measurement in another field and interpret that. We can't predict the magnitude of change, and we can't use these measurements to give a manager guidance about how they should adjust their practices. We're not at that level of understanding. And finally, at the bottom of this graphic, it's rare that researchers have tried to make an explicit connection between measures of, say, soil organic matter or infiltration or biological activity and connect that to downstream water quality. When they have, it's usually at the edge of field or perhaps in a subsurface drainage system. But we haven't really figured out how to summarize that across a larger watershed for watershed management purposes. Why is it important to answer these questions? At this point, I'm looking for suggestions from all of you. What are the ways that we can leverage soil health to manage water resources, both quality and quantity? And here's a couple of ideas I've had. Perhaps we could use soil health measures to assess whether implemented practices are indeed having the functional benefits that we expect. So if we have a program of implementing certain practices, we may very well be able to measure soil changes before we can measure the changes and impacts of this in stream. And the second item, perhaps we could use soil health measures to identify those parts of the watershed with the greatest potential to store water in the soil or to mitigate contamination movement and so on, and just based on soil properties to use those to target. In both cases, we need to do more to measure soil health and summarize soil properties across a watershed so we compare soil to water. What would you add? What do you want to learn on this topic? I will be happy to take questions and comments. My email address is on this slide, and I'll add a quick note here. We're organizing a soil health water quality symposium, which will be sponsored by UCAW, or the University's Council on Water Resources. It's going to be on November 16th, and we're also organizing a special journal publication on this topic. So contact me if you're interested in that.